All right, I'm back. We're on page 313, and we're just going to keep going with this derivative stuff. We're talking about first derivatives. What are we talking about here? Piecewise functions, increasing, decreasing, concave up, concave down, critical points. A lot going on. Had to refresh my memory there because it's a different day. All right, so first thing we want to talk about here is something called Fermat's theorem on local extrema. So you'll notice here it says Fermat. That's too tiny. Let's make that bigger. There. Let's try this. All right, that's pretty good. Fermat had a lot more than just a last theorem, so what I recommend is if you're interested in math at all, which you probably are if you're watching these videos, give a Google search for Fermat's last theorem. It's a really cool story of mathematics, which I don't have the time for here, nor do I remember exactly all the details. But basically, he kind of like scribbled in the edge of a book that a to the n plus b to the n equals c to the n has like no, I can't remember if it's just integer solutions or no solutions, maybe potentially, for n greater than 2, right? So if n equals 2, then this is the Pythagorean theorem, and there's, an infinite number of solutions. And then he said, so there are no solutions when n is greater than 2. And also, he just didn't have room to write it in the book. And so there you go, math mystery set off for hundreds of years. Eventually it was proved, but using math that didn't exist at the time. So who knows? Fermat was like super smart. He may have had something very clever going on that no one else has come up with yet. We just don't know. Anyway, for our purposes, we are interested in Fermat's theorem on local extrema. And this theorem says, if f of c is a local min or max, then c is a critical point of f. So this is a big deal. So what does this mean for us? It means that when we're searching, when we're out hunting for maximums and minimums, we should really look for critical points, right? So not every critical point will be a maximum or minimum, but every local maximum or minimum will be a critical point. So we're back to our horse thing again. So it's here. Not all critical points lead to local extrema, but all local extrema are critical points. So all horses have 4 legs, but not all 4-legged things are horses, blah, blah, blah. Okay, so you probably won't remember the name of this, and that's totally fine. The next time it'll maybe come up is in Calc 3, when it turns out that this extends to more than 2 dimensions. But you won't remember the name then either, so it doesn't make a difference. So the next thing, there's a lot of things. The next thing is the extreme values on a closed interval. So this one's a big deal because it's going to tell us exactly how to find these things. So assume that f of x is continuous on the closed interval from a to b. F of c is a minimum or maximum. Then c is either a critical point or it's one of the endpoints. So this is a giant idea. And we're going to combine this information with Fermat's theorem, kind of, to get what's called the candidates test. So this is the biggest test that we've learned so far. You're going to use it like all the time. So the candidates test is a way of finding the absolute maximum and absolute minimum of a function. So here's what you do. You're going to evaluate, I don't really do it in this order, by the way, but evaluate the function at the endpoints, find the critical points. So really, the steps are, you find the critical points on the interval, you make a table, you have the endpoints and the critical points in the table. You figure out the value of the function at each of those, and then whichever one is the biggest function value is the absolute maximum. Whichever one is the smallest function value in your table has to be the absolute minimum. So that's basically what we're doing. This is, you're going to reference this by name. So this one you actually do need to know. So let's see, let's go around the edge here. This nice color, kind of an Eastery color. All right, so you are going to reference this by name, so you have to know the name. Reference by name. Okay, so let's see if we can do it. So the candidates test. So let's find the extreme values. So now notice, for you to use the candidates test, I don't think it actually says it in here, but it should. The function must be continuous. So why must it be continuous? Because we're basically utilizing, we're using the extreme values on a closed interval concept. So for that to apply, the function needs to be continuous. So step one of using the candidates test is always going to be that you say the function is continuous. So here we go. F of x is continuous on 0, 6. So it's a polynomial. Polynomials are continuous everywhere, so we can actually just like state that. Therefore, by candidates test, I always feel like candidates test should be like possessive somehow, like the candidates own the test, or it could be like the single candidate parenthesis apostrophe s, like the candidate owns the test, but it's just candidates, like there's multiple candidates. By candidates test, absolute max min at endpoint. So we know the endpoints are 0 and 6, or critical point. Okay, let's find the critical points. So I need to see the function to be able to do that. F prime of x equals 6x squared minus 30x plus 24. Okay, I'm going to take a 6 out and then factor this thing. 6x squared minus 5x plus 4. Okay, so f prime of x is 6, and then x minus 4, x minus 1. If you can't factor, go back and practice factoring. I mean, it's like a really important skill. It comes up all the time. People are like, oh, it doesn't matter if you can do it or not. Like, it matters. If you can't do it, you're just going to be that much slower than everyone else who can do it. And they're going to have so much extra time to think through the problem, which is like a big part of calculus. So make sure you can do it. So x is 4, x is 1. Okay, these are our critical points. Our endpoints are 0 and 6. So now what we do is we make a table with x and f of x. Okay, so 0 is an endpoint, 1 and 4 are critical points, and 6. All right, now I need to take these values and sub them into the function. This is going to be kind of like just terrible. 0 is not bad, so 0 gives me 7. Actually, maybe none of them are bad. 1, if I plug in 1, I get 2 minus 15 is negative 13, plus 24 is 11, and then plus 7 is 18. So I get 18 there. Okay, and then I need to sub in 4 and I need to sub in 6. Both of those seem bad. Let's review synthetic substitution. So synthetic substitution is, it's like basically synthetic division, but you're really interested in the remainder. So you're basically using the remainder theorem. It says that when you divide a polynomial by like x minus r, the remainder is f of r, which is why when you get a remainder of 0, you're like, oh, it went in evenly. It's because when you plug in the value, you just get 0 because it goes in evenly. So I'm going to do that here. So here's how I set that up. I'm going to put 4 here, goes in the box, and then the coefficients. So 2, negative 15, 24, and 7. And I would use placeholders if I needed them. Okay. We drop down the 2, we multiply, we get 8. We add down to get negative 7, we multiply to get negative 28. We add down to get negative 4, we multiply to get negative 16, we add down to get negative 9. So f of 4 is negative 9. Okay, I'm going to do it again with 6. So I'm going to do it over here. So 6, and then it's 2, negative 15, 24, and 7. All right. This is like one of those archaic skills that like you always think like when you're learning it, like when will I ever? It turns out in calculus you will sometimes, because in calculus you need to do things without a calculator and it's just more convenient. 12, negative 3, negative 18, 6, 36, 43. So I get 43 there. All right, so 43. I'm going to check this on a calculator anyway, but we've said f of x is continuous on 0 to 6 by candidates test. Absolute max min is at an endpoint or a critical point. We then found the critical points. We made a table of values. For the table, we subbed in each of the values into f of x. From the table, the smallest value that I found was -9 and the biggest was 43. So I'm going to say, therefore, the absolute min is -9, and that occurs at x equals 4, and the absolute max, kind of inconsistent with the periods for abbreviations. I don't think it really matters. Is 43, and that occurs at x equals 6. So we got an absolute minimum that's occurring at a critical point. We got an absolute maximum that's occurring at an endpoint. So remember, endpoints can't be relative extrema, because for it to be a relative extrema, it needs to be the biggest or smallest value in an open interval that contains that particular number. And 6 is an endpoint. It's not a part of an open interval, right? You can't get to the right of 6 for this function. So that's what I'm going to go with for my answer. What I'm going to do is switch over to the calculator and just see if the calculator agrees. It's always a good idea to check that out. So let's see. And we have seen, usually it's at the end of a video. I don't know if it's at the end of a video because it takes so long to fix the mistakes. But I often do make mistakes at or near the ends of the videos. It's kind of what's going on with that? Probably, am I tired? Maybe. All right, so let's see. F of 0, f of 1, f of 4, f of 6. Yeah, synthetic substitution came through for us. Now, is it correct? Let's see. Let's graph f of x. So we only want to graph between, I'm going to go -1 to, no, I'm going to go 0 to 6, actually. I was going to go -1 to 7, give myself a little room on each side, but I didn't want to do that. And then I'm going to go -10, which is 1 less than what I think the minimum is, and then 44, which I think is 1 more than what I think the maximum is. And you can see this definitely looks right? Relative maximum here, but not the absolute maximum. An endpoint, which is fine. Relative minimum, also the absolute minimum. And then here, absolute maximum, not a relative maximum. So perfect. Candidates test is actually going to work every time. And as I mentioned, you're going to use it a lot. All right, I'm going to do this next. Actually, you know what I'm going to do? I'm going to stop this here, and I will come back and do the next problem in another video because I'm not sure how in-depth I want to go with it. And if I go in-depth, it's going to take a little while. And if I don't, it's not. And neither of those is particularly bad. But I'm going to stop this here, and I will see you in the next video.